Hello, everyone. My name is Lee from Stony Brook University's Physics Department and Brookhaven National Laboratory. It's my great pleasure to introduce Dr. Mark Ritter. He is chair of the Physical Science Council, which supports basic physics science research in IBM's Zurich, Yorktown, and Hamilton labs. The IBM Quantum Experience was launched by a group he led in May 2016, allowing users to access a program of 5-qubit quantum processor from the cloud. He has been an active advocate of quantum science funding in the USA. He's a member of the National Quantum Initiative Advisory Committee and has served on the first governing board of the Quantum Economic Development Consortium. Dr. Ritter was the recipient of the 1982 American Physical Society EPCA Award for his work on the optic and magnetic properties of solids. Dr. Ritter received his PhD in applied physics from Yale University in 1987. Welcome, Dr. Ritter, and the floor is yours.
Thank you very much. I'll just share my screen here and make sure it, like before, you can see everything. There we go. All right. So let me talk about the qubit challenge, which is how we make qubits that are good enough that we can use them in quantum computations that would give advantage or be better than classical computations. So let's continue here. And again, what is the promise? I'll go through this very quickly, and I'm giving just a 50,000 foot overview for people that may not be familiar. And why are good qubits so hard to make? I hope to show that there are many types of qubits, and they all have their challenges due to different physical implementations and the physics of those implementations. Finally, I'll say something about the outlook, what I think is going to happen. But the basics are, and Charlie Bennett kind of came up with this wording, the rules of quantum computing are we're trying to use the rules of quantum mechanics, so that a physical system can, even though it's in a definite state, it can behave randomly. And this has to do with superposition of states in a quantum object. And it is somewhat related to Heisenberg uncertainty principle, but especially to the principle that you cannot know what state the qubit is in, and they're incompatible measurements. That is, you can look at it one way and it can yield reproducible results, and another way it looks stochastic. But that's perfectly normal in the quantum world. And the second thing is two systems that are too far apart to influence each other can nevertheless behave in ways that, though individually look random, yet if you measure them again and again, you see they're perfectly correlated. And that's this entanglement principle. And there's one more that I'll mention along the way, which is interference. But any quantum computers exploit these two principles for computation. And again, the basic thing in the way I describe this is for people who are used to regular qubit or regular digital bits, is that qubits, the state space of qubits grows exponentially with the number of qubits, so that with 90 qubits, for example, you would have as many states as there are atoms in the planet Earth. And with 300 qubits, you could have more simultaneous states represented than the number of atoms in the universe. The question is how we exploit these states. And people will say, well, I can have 64 bits or 300 bits. Yes, but with 64 bits, you represent 1 out of 2 to the 64th states. Whereas with qubits, you represent them all simultaneously, given that principle of superposition. So how do we exploit these states? There are problems that classical computers cannot solve. The ones that are easy are called polynomial problems, and they scale polynomially with the number of, let me just put on the laser pointer, they scale polynomially with the number of devices. And okay, hold on. And then there are, yeah, so here, polynomial scaling problems. And then there are problems that scale exponentially that we have to we have to solve in a different way. Yeah, sorry, here. So those problems are the ones that we want to attack with quantum computing. And from what we're looking at, quantum computers exploiting this exponential state space actually have a different set of problems that they might be able to solve in polynomial time. We know the polynomial bubble of quantum computers extends beyond that of classical computers, but Charlie Bennett and others early on showed that quantum computers cannot solve all the NP-hard problems in polynomial time. But as recently as 2018, Raz and Tal at Princeton showed that there was a problem called a non-oracular Bernstein-Vazirani problem that could be solved with one query by a perfect quantum machine that would take an exponential number of queries for a regular computer. That's outside the P hierarchy altogether. And they've proven that with the complexity theory. So the question remains, and it's a problem that various people will be addressing in their research over the next decades, is what other types of useful problems remain in here? Whereas this Raz and Tal problem is purely academic right now, we would like to find problems that aren't just academic. So how do we describe a qubit state? I'm sorry for those who already know this, but a qubit is a binary object. It can be either in the state 0 or the state 1. And if we represent the states of a qubit by a unit radius sphere, 0 at the North Pole, 1 at the South Pole, then the state of a qubit can be described by a linear combination of 0 and 1, constrained to lie on that unit radius circle. And this is simply a spherical coordinate representation of the coefficients of this qubit, so that anywhere other than the North or South Pole represents some definite superposition of 0 and 1. And to do quantum computing, I have to be able to control that state and maintain that state as long as I haven't touched it with my quantum computer. So keep that in mind. Dave DiVincenzo in year 2000, came up with a number of criteria that any good quantum technology that we would use for digital quantum computing would have to meet. And the first is a well-defined qubit states. In this case, the 0 and 1, separated by an energy difference that's greater than kBt, enough greater that 0 and 1 aren't thermally disturbed and shouldn't be disturbed by other factors in the environment either. The second thing would be initialization to a pure state, like we initialize registers in classical programming. But here I have to initialize reliably all the qubits, say to the 0 state. Then we have to have a universal set of quantum gates, gates that allow us to not only explore all the states in the quantum, in the Bloch sphere, all the quantum states that we might want to use, and those would be single qubit gates, but also entangling gates. And here I show a 2 qubit gate, though there are gates between higher numbers of qubits. Those higher number of qubit entangling gates are even harder to effect. So it can be shown that with just single qubit and 2 qubit gates, you can do any algorithm you would like to do. It's a Turing complete set of gates. It's a universal computer. The fourth thing is qubit specific measurement. We'll be talking about algorithms, and you've seen some of them, for example, in Steve Gervin's talk this morning, where you want to measure a particular qubit out of the set of qubits and perhaps not disturb the others. So that qubit specific measurement is useful and needed. And finally, a long coherence time. And physicists borrowing from nuclear magnetic resonance terminology talk about T1, which is the lifetime of relaxation. If you put a qubit in the 1 state, how long it takes to relax to the 0 state. And T2, which has something to do with that theta dependence, and that is where it is on the Bloch circle, crudely speaking. And that both of those 2 times must be much longer than the time to do quantum operations on a qubit. Say 10,000 times or greater ratio It's not the raw coherence time that's important, it's this ratio that's important. And so keep that in mind as we look at the different qubit technologies. And the way we represent quantum circuits, and I've traced this back to a paper by Feynman in 1985, perhaps it came before that, but that's where I found it, is representing the qubits as lines. And on that line, which represents time, you start in some initial state, you have single qubit and 2 qubit gates between those qubits which can have 2 qubit gates. And finally, you have measurements. So this set of gates represents a quantum circuit, which then allows you to do a particular algorithm. So that's very high level, and I'm sorry if this is too high level for many, and people know this, but again, quantum algorithms, and this is a hand-waving argument, but the first part of the algorithm is to make this superposition of all 2 to the n states simultaneously by applying Hadamard gates that puts them in superposition. And then we encode the problem into these states, which in a hand-waving way are phases on all these qubit states, and also entangle them. And the entanglement also comes along with some interference between the qubit states. And those states which give constructive interference are amplified, and destructive interference destroys other states. And the answer would be those states which have been amplified the most, because when you measure the qubits later, the amplified states will be those that you measure the most. And this is a hand-waving argument. And in Charlie Bennett's way of thinking, it's like a 2-slit experiment, and having coherent light come in and create an interference pattern. With 2 slits, you can resolve the separation of those interference pattern, which tells you about the slit separation. If you had n slits, just like n qubits, all separated the same amount, those interference peaks would be very sharp. It would tell you much more accurately what this separation of the slits is. And so that interference part of qubits is used to actually perform algorithms. So for those of you who haven't thought about this, it's very, very different than regular computers. So that's enough of this high-level overview. What I want to do really is dig into some of these qubit technologies. And there are 5 here. There's one more I'll mention, which people are searching for a qubit. The first is superconducting qubits, and those come in various flavors. The transmon invented at Yale, fluxonium, phase qubits, and capacitively shunted flux qubits, and various other types of qubits that people have tried with superconducting circuits. Second would be trapped ions or neutral atoms. And here I show some of the ion species, but other people are using neutral atoms. The qubits behave in similar ways, so I'll just describe ions. The third type is engineered defects in solids, like, for example, phosphorus atoms in isotopically pure silicon, nitrogen vacancy centers in diamond, or dimers in silicon carbide. Those are 3 examples of engineered defects. The fourth is spins or quantum dots. Of all these qubits, this is the only type of qubit. It's truly only a 2-state qubit if it uses a single electron. And I'll talk about spins and where we are with spins. And finally, I will talk about photonic qubits, and that use single photons. They're polarized or squeezed and made to interact at beam splitters or these virtual beam splitters in array waveguides. All of these technologies require cryogenics. Now, the photonic people will say, no, my qubits are room temperature, but actually they need cryogenic single photon detectors. So none of these technologies can get away from using cryogenics. And I'll talk about that some as I discuss these qubits. And this discussion will be more like from an experimentalist point of view. What are the warts on the different qubits that make them very hard to perfect? In fact, there are limits, fundamental limits on the qubit reliability based just by quantum mechanics. But I'm going to show some of the different physical mechanisms that make it very hard to make each of these types of qubits. And I'll start with trapped ions, and neutral atoms are similar. This is ytterbium-171, and you can see the energy level diagram of this atom. The qubit states are these 2s1/2 states, the ground states of the ion. Those are the ones we want to use with the orbital angular momentum F equals 1, F equals 0 shown here. And the states actually may look strange to you. The one state, orbital angular momentum up, is the one state. The 0 state is down, but there's a second number here, and that has to do with the vibrational quanta state. We'll come to that. So 1 is the spin state, is what we want to use for our qubit, but the vibrational quanta come in useful for things like 2-qubit entanglement gates. But you have this constellation of other energy levels in this ion, and every ion will have a different set of levels. What makes ion-based quantum computing very challenging, in my view, to scale is that as you load these ions in the traps, they can get into some of these other states that are, in some cases, metastable, and you'll need other laser wavelengths or other electromagnetic energy to kick them out of those metastable states back into the ground state. And so all these wavelengths here, you might need in your apparatus in order to put your set of ions into the right ground state levels. And now I'll describe how the qubit is actually programmed and used, and you'll see that it's a very interesting beast. First, the coherence times. Now I'll just give the good ion qubit coherence times. Typically T1 and T2 can be on the order of 2.5 to 25 seconds. So this is a very good coherence time. But in cases where people have made atomic clocks with some greater effort, up to 15-minute coherence times have been achieved. But now remember what I said about the gate time and measurement time. I didn't say that, but obviously you need to measure the qubits at the end. Some gates are like the Mollmer-Sorensen gate, which I'll describe, are on the order of 100 microseconds. And the measurement times on the order of 500 microseconds or half a millisecond. And these times will affect the ultimate length of time you need to do some of the algorithms that we're envisioning we would use with these ions in the future. So again, this ground state are the states of the qubit which we want to use, and there is some field dependence to the ground state, so they're slightly sensitive to magnetic field and need to be shielded for that reason. Now, we have to cool these ions because, as you saw, that ground state was only 12 gigahertz separation, which is an order of half a degree Kelvin, kBT. So if you have the ion in an environment where it has radiation that's higher temperature than that, it will destroy the quantum state. And the vibrations are actually phononic movements of the ions. They're moving in space in the trap, which I'll describe, an electromagnetic trap. And you try to hold them still, but they can still have center of mass motion. And those are phonons. You need to cool them down before you use them to temperatures below that effective half degree Kelvin. And what is used is Raman cooling. You pump the ions, and this is a single ion, and you see the 0 state and the 1 state, and then you see 1 phonon, 2 phonons, 3 phonons, 4 phonons. So it's vibrational energy in the 2-qubit, 2-ion system. And you pump it to the red of the 0-1 transition and have this anti-Stokes-Raman cooling, where if you pump it to the red, instead of pumping this whole energy level, you pump just below it, then that phonon will be absorbed and re-emitted, and you'll end up in 1 phonon less. And if you keep bathing it in this same light that's around or a little bit less than 369 nanometers, which is in the UV, then it will eventually end up in the 0 phonon state, vibrationless and microkelvin, really, temperatures effectively. So you have to cool all the ions in your ion trap. next, how do you control the qubit once it's in the ground state? Well, you use 1 qubit gates, again, that start with the ion, say in some state like the 0 state, spin down, and you have a 355 nanometer excitation. Sorry about that. When people ping me, I get an issue with my computer. 355 nanometer excitation, which is virtual transition. That's more energy needed than to go to the 2p1/2 state. And by having the right duration of that 355 nanometer excitation, you can control, do an X gate, which means move from 0 to 1, or you can put it in a superposition state. And the fidelity of those gates is greater than 99.99%. They're highly accurate as any qubit we now have. Then the next thing you would want to do is, oh, that's a single qubit gate. What about 2 qubit gates? This is what's called the Mortimer-Sorensen gate. And what you do is you have 2 ions. And again, their state is represented here by S's and D's. You want to go, say, from spin down on both ions to spin up on both ions and entangle them in doing so. And what's happened here is that you have 2 co-propagating lasers that have a slightly different energy, so that you need both of them to make the transition. And these excite a center of mass or breathing mode in those ions, such that you're mediating the dipole coupling between the 2 ions and causing one to flip to some intermediate state. And then it changes the state of the other one, and it also becomes entangled. So you go from this state to the SS state through one of these intermediate states to the DD state, for example. And so this gives you an idea of the Mortimer-Sorensen gate. Now, if you're in the ground state with n equals 0, you can only go through the n+1 transition. But if you're in another vibrational state, you can go through one of these other transitions, which are equivalent. And the fidelity is 99.97 or some percent, something like that, for 2 ions. But again, many of these quotes of the fidelity of the ions is for only 2. Once you add more ions, the fidelity is poorer. In recent experiments that IonQ has published, the fidelity of 2 qubit gates with controlled laser beams causing single and 2 qubit gates is only on the order of 98% or so, maybe 99, but not 99.9, because of all the beam steering electronics and the motion of the ion within the beam, because it's not perfectly stable in its trap. And in fact, you're exciting these breathing modes. As it vibrates in the laser beam, you're changing the intensity and hence the quantum operation. So these are wrinkles in the experiment that ions will have to overcome. You can look more at the original papers of these type of gates. And I want to make the point here, as you look at these papers, I'm not giving necessarily the first papers that describe these technologies, but useful papers to those who want to explore them. And so, yeah, now let me go ahead here to the next. So how do you measure these ions? If they're in some trap, and I show here a linear Paul trap, which I'll describe in the next chart, you have a row of ions, you bathe them in light that's designed to cause the ion to fluoresce if it's in the 1 state. That's light at 369 nanometer wavelength. And it's a non-destructive measurement. So it's non-demolition in the sense that you can have this light bathing all of your ions together. Only those that are in the 1 state fluoresce, and then you simply count the number of ions fluorescing over time, and that's why it takes about 500 microseconds, but it gives you 99% or so fidelity. The ions that are in the 0 state remain dark. Like if there was an ion here that I'm pointing to the left of all these bright spots, and that would be in the 0 state. And all the rest of these ions are in the 1 state because they're fluorescing. And so that's how ions are measured. And why it takes the time is the ions, of course, emit in 4 pi steradian. So you're collecting only some fraction of the emission with your CCD or other detector. And I'll make some comments on that in just a bit. That's one of the limitations, that the speed of collection is limited by the angular substance of the emission that you can capture for an ion. So that's how they're measured. And how are they trapped or controlled? The original trap is described as a linear Paul trap, and it was described early on, and I give some of the early papers on this. And what it consists of is a series of rods or electrodes and an AC electric field given to these electrons. And at the end, there is a positive charge electrodes that create a barrier so the positively charged ions can't come out of this bathtub trap. It looks like a bathtub along the direction of the linear trap. And that causes the ions to string out in a line like a bead of pearls. And so what does this look like in cross-section, though, if I cut through it this way in the XY plane instead of looking in the Z direction, which is along the trap? In the XY plane, I excite with an RF electric field the opposing the X and Y direction electrodes. And in this example, I've frozen it when the E field in X direction is positive. So it's repelling the ion in the X direction, and in the Y direction it's negative. So it's attracting. So then you reverse this field quickly enough that the ion stays in the center between all of these electrodes. And typical resonant frequencies for these traps and keeping the ions there is on the order of tens of megahertz, like 50 megahertz or something like that. And the ions are actually not exactly stable because you can't stably control an positively charged particle. You have to have this RF trap, and they're executing tiny little motions there. Okay, and you have to keep that in mind as you try to interrogate them with a laser beam. That laser can't have a very, very tiny waist, or the ion will be moving around and the E field it sees will be changing. So that's a comment here on the traps and how close you can put the ions. And people have been clever. I think it was Sandia, managed, of course, by Honeywell, who have first created these traps, and they created them out of a 3DI silicon, etched silicon, where they unrolled the 4 electrodes of the linear Paul trap to have 2 on each side of this center line. And again, an RF field, and that field is controlled by diffused contacts coming up through the silicon that touch these different electrodes, as well as there are little electrodes on either end so they can shuttle the ions around and change their order if they wish. And I won't get into that, but people are becoming very clever using and designing these traps. But right now, let's imagine a chain of atoms, of ions here, about 20 ions long, held above that silicon substrate. And then the laser beam comes parallel to this substrate. It's etched so the beam doesn't touch the substrate and scatter. So away from the beam waist, it's etched down to allow the wider beams to enter this trap without touching it. And so you see, you have to cool the ions with DC laser light, pop it out of different excited state, metastable states with even different frequencies. So you need many different frequencies of laser light. Then you control them with laser pulses precisely tuned for single qubit gates, or with 2 co-propagating pulses for doing the entanglement. You measure them by yet another wavelength to cause DC fluorescence of the 1 state only, and measure with a CCD. So you need multiple laser wavelengths, some pulsed, some DC, and you need a structure which will support a stable control of the position of the ions. So it's a beautiful but a difficult technology. Hello, can people go on mute here? Hello, can you hear me, Dimitri? Yeah.
Yes, we can hear you.
Okay.
I'm trying to find where the sound is coming from.
You can simply mute everyone and then unmute me again. It's probably the easiest way.
Let me do that.
Yeah. All right, just let me know when things are back.
Yes.
Good.
Okay.
So engineered defects. Now, these are types of defects like phosphorus ions and isotopically pure silicon, nitrogen vacancy centers in diamond or dimers in silicon carbide. And by engineering, I mean, for example, nitrogen vacancies in diamond are through ion implantation of nitrogen through a mask into a diamond substrate. But I'm going to describe one that's a very beautiful scheme that uses a scanning tunneling microscope and an atomic mass to fabricate phosphorus ions in silicon. And describing this will describe to you some of the issues with all of the defect-based qubits. You can use electronic states of these defects or nuclear states or both, and you can move the electronic qubit state into the nuclear state for storage, because nuclear states typically are more have a longer T1, T2 than electronic states, just because they have a much smaller magnetic dipole moment than the electric dipole state. So they're harder to influence. So what did Michelle Simmons do here and her team at University of New South Wales and what they actually did was start with isotopically pure overgrown 28 silicon. The reason they had to do this is silicon 29 has a dipole moment in its nucleus. And so that magnetic dipole moment, though small compared to an electron, will upset the quantum state of the phosphorus ion, both its nuclear and electronic state. And it's a path of decoherence. So you have to grow isotopically pure 28 silicon, which has no nuclear moment. And once you grow that, you can dip it into HF, hydrofluoric acid. That coats the surface with hydrogen atoms. In ultra-high vacuum, you desorb some of these hydrogen atoms with a scanning tunneling microscope tip. And after you've desorbed the atoms where you want to put phosphorus, you dose that chamber with phosphine gas, and that will bind at the site you've desorbed. And then you remove the hydrogen mask and overgrow isotopically pure 28 silicon. You have to overgrow it because these phosphorus atoms would be sensitive to anything that might fall onto the surface or be absorbed onto the surface. So you need to protect it again with this isotopically pure encapsulation. It's a beautiful process. And here's what you get from this process, again, from Michelle Simmons' team. Each qubit, in this case, has 2 phosphorus atoms shown below in a scanning tunneling microscope view at the bottom left. These are separated by 8 lattice constants, or 8 atoms, in order to create a singlet triplet state qubit out of those electronic states. And here it's shown in the figure above in a schematic view. And then to the right is a larger area view where they've panned out the 2 square dotted things in the center that have like the D2U and D2L are the 2 phosphorus atoms that represent 1 qubit on the right side. And the left side, again, has 2 phosphorus atoms creating a qubit. And then these other lines are actually very dense lines of phosphorus atoms where they've drawn many phosphorus atoms in a plane. And what Michelle told me is they find that at 4 degrees Kelvin, these lines become very metallic. And so they conduct electricity very well. And they're used to bring the pulses in that control these qubits and cause their interaction. So here you see these 2 qubits have to be within about 60 or maybe 200 on that range, 60 to 200 lattice constants apart, in order for the small electric dipole moment to interact and cause entanglement. So this gives you an idea of the number of electrodes required for this technology and how it's fabricated. And now let's move on to quantum dots or spins. Now, these are beautiful examples. This is from Petta's group at Princeton, who has some beautiful, Jason has some beautiful work on quantum dots. And what these consist of, if you look in the center picture, is, in this case, two quantum wells that can hold only one electron each. And that's mediated and controlled by this complex series of gates above them to create quantum wells that will hold only one electron. Shown to the left is what those gates look like with false color under a scanning electron microscope picture. And you see the two qubits, or the two spins or electrons, will be held in their two wells pretty close together. And to control them, you have electron spin resonance, or RF energy, at their energy to control the state of that electron. To cause them to become entangled, you control the middle gate of this pair of wells to lower the barrier height and let the electrons move closer together. Of course, they repel each other because they're both negative charge, but they can move a little closer together, and there's a strong dependence of the electron spin-spin interaction on distance. So that mediating gate in the M there controls the entanglement. And the right side here, what you see is what's called the stability diagram for these two qubit wells. And what it shows is if the wells are very shallow, a single electron can't fit in either of them. Just because of the finite temperature, it gets knocked out of the well. As you increase the right well depth with the voltage you apply, soon it will load a single electron in the right well. Then you increase the left well depth, and now a single electron loads in the left well. And that's why you see these two designations here: 0 electrons left, 0 right, 0 left, 1 right, and 1 left, 1 right. So this is a stability diagram. And this actually goes to a very high number of electrons. If you have very deep wells, of course, you can have more electrons. But for a qubit, we want just one. And the beautiful thing is that these qubits in a magnetic field are truly binary systems that only have two states. However, if the magnetic field you apply on this device is the same for the left and the right qubit, they're indistinguishable, since the Zeeman energy is just dependent on the magnetic field that each spin sees. So you need to apply an external field that has a field gradient. So each qubit will have a different Zeeman splitting. And that has to be a gradient across these very small distances. This is not so easy to do. And some people have put micromagnets near the device in order to cause that to happen. But that's a thing to keep in mind. This picture doesn't show where that magnetic field is being applied. And you must do that in order to make the qubits distinguishable, or else you will not be able to do any algorithm. Now let's look at how this qubit is controlled and measured. Again, looking at the stability diagram, we start with both wells empty. That's the upper left picture where there's a field on, and the two qubits have a different energy in the field because that magnetic field at each qubit is different. But the wells are too shallow to hold an electron. So you increase the voltage on the right well, the positive voltage, until it becomes favorable to allow a single electron to hop into that well. And it always comes in the down position. If you do this very slowly, it'll load in the down, spin down, or 0 position. Then you initialize the left cell doing the same thing, and it loads in the spin down position. Now, as I said, since the two qubits have different Zeeman energy, they're controlled by different RF frequencies. You can actually control them simultaneously with two RF frequencies, one tuned to each qubit And essentially you're doing electron spin resonance to drive the qubits around the Bloch sphere to the point you want them. That's a single qubit gate. And then you do some of the 2 qubit gates by changing that, that mediating or plunger gate in the center to change the separation of the 2 qubits. To measure them, you now reduce the depth of the well. And if you do that in the left gate first, even if this qubit were in superposition, so it were a combination of down and up, at measurement time, as you're slowly increasing the or decreasing the positive voltage, so the well empties, it will resolve in either the up or the down state, which you know which state it's in by the voltage on the gate when that electron hops out. Likewise, you empty the left and the right and measure them, and now they're both empty and you can start this process over again. So that's how a spin qubit works. And now you could see from this diagram that it's pretty crowded to get all these gates and measuring islands there, so that you can measure that charge pulse from a single electron transistor and know at which voltage it is emptied, what state the qubit is in. So the spin qubits, though, how can you couple more together rather than crowding all these electrodes into a small space to get more than 2 qubits? Well, Jason Pettis' group again said, well, I can couple an antenna to one of these spin qubits. And this shows an antenna. And now the spin qubit's a tiny thing here, showing an inset. And now that antenna couples to a transmission line. And the idea is if you can couple RF to these qubits, then you can have another set of qubits over on that large transmission line somewhere else. It's not easy, and they're working hard to make this type of coupling more effective, so that they can actually make multi-qubit machine more than 2 qubits. And another problem with the spins is how are we going to place a gradient magnetic field at each spin that's in a, say, a square lattice of spins that's a different field for each neighboring qubit? That's kind of hard. So some people have said, well, I can create a spin qubit using 3 wells, and again, a singlet triplet qubit, and I can control them with energies in these 3 wells so that I don't need a magnetic field. And the problem is now you have a lot more wires and a lot more connections, and it just exacerbates what I call the escape problem, or escaping all the signals you need from the spins. So this is not easy. Superconducting devices, Steve Gervin talked about these, and these transmons that all show that IBM uses were invented at Yale. Is shown here on a circuit. There's a qubit. It's a superconducting qubit consisting of that the Josephson junction in parallel with a capacitor that creates a nonlinear potential. And you have many states, not just 2, like the electron spin. You have a series of states in the case of the transmon drawing closer together. And we use only the 0 and 1 state for the computation space. And the frequency is on the order of 5 to 6 gigahertz, which is on the order of 240 millikelvin. That's why they have to be on the order of 20 millikelvin or below to keep the temperature far below the ambient temperature. And they're connected via capacitively coupled transmission lines. They're resonant at a different frequency. It has to be at a different frequency, or the lines would be like antennas, just to couple the qubit state out of the qubit. And that would have 0 lifetime, basically. So they have to be different frequencies, and the different qubits connected on that transmission line have to be at different frequencies. And they're controlled just by RF pulses, like this diagram here. Some RF pulse causes the state of the qubit to go from the 0 to the 1 state. This is an X gate, just rotating down the direct X-axis of the Bloch sphere and causing the qubit to go to the 1 state. And likewise, the 2 qubit states have a Hamiltonian. Don't have time to describe this, this Hamiltonian, but it has a term in it which has the 2 qubit interaction over some energy times a ZX. In other words, the qubit that's controlling the other qubit is hit with RF radiation that's actually not at its resonant frequency, but at the resonant frequency of the qubit that you want to entangle with it. And that's called the target qubit. And when you do that, you get this strange interaction here. And here's a plot of what that looks like. If the control qubit's in a superposition state, it causes the target qubit to end up in a superposition, but in the X, like an X rotation superposition of that original control state. That's why the minus ZX. You go in the minus direction here and so forth. So this is the Hamiltonian that causes what's called a cross resonance gate that also was invented at Yale. And here's a whole lattice of 16 qubits. Some of these are available on the web for people to use through Qiskit. And the lattice is a 2x8 set of qubits connected together by these transmission lines. So the light blue lines are these bus resonators or capacitive coupled transmission lines with, say, these Q4 and Q5 coupled there. And all these neighboring qubits, say Q4 to Q3 and Q5 and Q13, those 4 qubits have to have different frequencies or you can't distinguish them and they're useless for computation. So that's a challenge for superconducting qubits because controlling that frequency depends on controlling this tunnel junction, which is quite variable. So, and this is what IBM quantum computer looks like. That qubit chip is down at the bottom of a cryostat. I'm sorry for this. I don't know why this is happening. And the control electronics are outside at room temperature. Now photons. I want to go through this because there's been a lot of recent press on photons. And people say, oh, they're room temperature qubits and have a long lifetime. Yes, that's true. But there's lots of issues with photonic quantum computing. You start with something like this. And this Envision paper, which is quoted at the bottom here, a very recent paper in Nature, they've shown photonic boson sampling in their device. And you start with squeezed states of light, or if you want to think about it, polarization states, which are different, but squeezed states can be used too. And they generate those with ring resonators, and they pass through a chip which has, in this case, 4 single photons coming in that are entangled, 4 entangled photons coming into this device where they have these on waveguide array beam splitters. And as they pass through these beam splitters and phase shifters, which are like a Mach-Zehnder interferometer phase shifter, they are made to execute an algorithm. And in the case of photonic quantum computing, the actual measurement is what gives you the answer. So you have to measure it, and those detectors have to be at cryogenic temperatures because right now we use superconducting nanowire single photon detectors. It's the most sensitive single photon detector that we have because you want to measure every one of these photons. You don't want to lose a lot of them. And so you need very, very sensitive detectors. And this above scheme, and one that China had a big fanfare about last year about showing supremacy, are not general purpose quantum computers yet. They're boson samplers, but people have made proposals on how to make a more complicated structure and control in order to achieve a universal quantum computer with these photonic type structures, but nothing has been made like that yet. And it still requires error correction. All of these would, because there are still errors. And in fact, another issue with these photonic computers is the fact that if you want a 4-qubit interaction, you have to have 4 entangled single photons. And this probability distribution to the right was that measured in the paper that I quote down at the bottom. The probability of generating 4 photons that are entangled, single photons, is about 10%, a little bit less. But the probability of generating more photons that you need for a quantum computation needing more qubits, since the photons of the qubit, drops off exponentially. So by the time you get to 18 photons, you're on the order of, you need to have on the order of 1 million tries at generating those photons in order to produce a 19 photon state. And so you only have production every 0.3 of a second. So it's very slow, and we don't know how to scale this yet. This is one of the problems of photonic computation, even if we generate a general purpose computer. And then here's the one that people are searching for, topological qubits. These have been mentioned before. It's looking for a Majorana bound state. People have looked at nanowires. I won't use names because of the embarrassment, but it's a nano-indium antimonide wire with some superconductor on it to have proximity, in this case aluminum, to proximatize the indium antimonide wire so it is a superconductor too. And at the ends of this nanowire are the Majorana bound states that represent the qubit. And I won't go into the idea. People have created a whole theory of how to braid, move these states around, which is how you do gates in Majorana systems. But the point is, no Majorana state has been conclusively demonstrated, and no qubit has been demonstrated. Even the recently retracted TU Delft paper is retracted that the conductance peaks they saw were consistent with Majorana states. And further, I'll mention to you the paper at the bottom here. Daniel Loss's group and others have shown that these topological qubits are still susceptible to decoherence by coupling to certain charge or other fluctuations. And so it's not a perfect qubit. It doesn't protect you from all environmental noise. But the idea is that if you could find a good topological qubit, perhaps you could reduce the error correction overhead. And that's why people are still looking for this, as some people might call it, a mythical qubit. So I'm going to summarize where things are today in qubit technologies. In all of these systems, we're going to have a hybrid system with conventional technology and control hardware controlling this quantum technology. And I'll have a chart on that at the very end, the next chart. All these technologies share similar issues, the 2 qubit gate fidelities and spectator errors. I didn't tell you what those were, but if you have a series of qubits, then when you're performing 2 qubit gates or even single qubit gates on a qubit, its neighbors can be influenced by the electromagnetic energy you use to change the qubit state or control the entanglement of 2 qubits. And the 2 qubit errors especially limit the useful technologies today. Now, the multi-qubit gate fidelities are often less than that quoted in this table, as I already mentioned. So I quote here about the best fidelities seen, not the fidelities you see in larger pieces of hardware with more qubits. And as well, I'm not showing here the variability of qubit states and lifetime, which has to be tackled as well. So there's a lot of engineering and science work to make the fidelities better, to make the variability less, to make a manufacturable technology. And in many cases, the RF and or laser control hardware, I think in every case, it's much, much greater than the size, weight, and power than the qubits themselves. So people that talk about the size of their qubits, it's totally irrelevant because the rest of the system components to support each qubit are far greater, orders of magnitude greater than the size of the qubit. And we don't see a way right now to scalably make this work for any of these technologies. There's no wrench rule. Every qubit needs to have an I/O. And so some multiplexing may be useful, but once you time multiplex and you don't have enough coherence lifetime, that limits what you can do too. So there's many trade-offs that people are working on. With that in mind, you see the ratio of T1 or T2 to T-gate. And it's that ratio which is important. And you see for 2 qubit gates and these first 4 technologies, superconducting qubits, ions, defects, and spins, you have quite a few gates you can do before you're just getting 50% probability of something, which is nothing. The 2-qubit gate fidelity is also pretty good in most of these now. These defects and spins have come up a long way against ions and superconducting qubits. But here, the speed, I point out to you, the speed is important because future algorithms could take billions or even trillions of steps. So if you're thousands to millions of times faster than other technologies, and that makes a big difference eventually to the algorithms you can perform in reasonable time. And I give some other metrics here and the key benefits. So I've talked about those. So I'll move on to the last two charts. The first one is one that Steve Gervin and Rob Sholkoff published in Nature. And this is a beautiful understanding, now that we've looked at these different qubits, of why the coupling rate, or how fast these gates are, is different for the different technologies. If you're looking at nuclear spins, the nuclear magnetic moment's very tiny. If you're looking at superconducting qubits, its electric dipole moment is huge because the structure is huge. The larger the dipole moment, the faster the 2-qubit gates and the coupling can occur. And so that's one important thing in these technologies. The other is the coherence times. If you can't interact with the nuclear spin, it takes a long time to decohere it because there's not a strong interaction with the environment. So these naturally have a long lifetime, whereas the qubits with a large dipole moment have a short lifetime. So, but it's the ratio, remember, of this, the T1 or 2 to T gate, that gives you the useful technology metric. And this describes then a lot of the features of the table I just showed you. And finally, and just pointing out a few things, and this is the last chart, a quantum computer, like I flashed on that one page, has many different aspects of science and engineering to perform the actual control of the quantum device. We've only been talking in this talk basically about these different quantum devices in that we are controlling, all cooled in some way or another. Well, those devices need some program, say an application, that needs to be resolved into a quantum circuit that I showed you. And then you need to resolve that into pulses and a scheduler of those pulses on the qubits. And that controls the control electronics, et cetera. And then you need to measure it. And so the inverse problem has to be solved. And Qiskit that IBM has covers all of this, software part, including back-end simulators and code comparing type of tools. And people have actually applied this to ions, like Rainer Blatt's team has used Qiskit to control his ions using this interface of the pulse interface up here, the pulse scheduler. And they've been able to do their ion computer control, because all of this stack needs to be together to actually have a quantum computer and control the device. So that's what I had to say. And there's some educational links at qiskit.org if people want to poke more into Qiskit, if there's any students on the line. With that, I'll stop and turn it over to the questions. Thank you.
Great. Thank you so much for this great lectures. Now we invite the audience to ask questions. You can raise your hands and you can type in the chat. So, any questions? I don't see anything from chat yet. Well, let me start with a very general questions too. Mm-hmm. So we know the superconducting qubit now is in the market, is building the quantum computers. How about the rest of them? What's the time scale? Say 5 years, we see anything out of the other concepts, traps or spins type of a qubit into the real computer you can buy?
Oh, right. So that's a good question. As you know, IonQ and Honeywell have invested hugely into the ion-based computers. They are actually getting some metrics better than superconducting qubits, but I haven't seen the actual published paper, say, from Honeywell yet. So I'm really not sure what was done there. And yet, as I described ions, the thing is that having only 20 or 40 or even 100 ions doesn't get you to the size of computer that would be useful, right, for doing algorithms that could show advantage over conventional computers. So that's an issue that all of them will have to resolve. And I see scaling ion-based computers or neutral atom computers to be very difficult for the reasons I pointed out. You have both RF energies, you have many laser frequencies, you do need to cool them. There is some debate about having cooled traps versus room temperature traps because you're cooling them with lasers and Raman cooling, but nevertheless. And so these are the top two contenders right now, but there's a huge amount of, let's say, ancillary technologies to be developed at reasonable cost and reliability in order to actually control ion-based computers. Then spins have made a huge advance in the recent past 3 to 5 years. Spins, the main thing is how do you get more than 2 or 4 or 8 spins? Because the number of electrodes is just so huge locally. How do you actually realistically escape all those signals to control the spins individually? That, to my mind, is the limiting thing with spins. I've talked about photons. You understand all those detectors are in a cryostat. So you have to run lots of signals to a cryostat to measure them. And engineered defects, we will see, but so far they haven't found a way either in order to couple multiple engineered defects in a way that seems convincing that it can scale. So right now, it looks like the ions and the superconducting qubits are the leading contenders. And we've tried to keep Qiskit very agnostic so we can run any system. If someone should find a beautiful topological qubit or something, or in the C2QA Center, we should find some superior superconducting qubit, we're ready for that.
Oh, that's great. That's very nice to hear that. So we have a question from David Liu. He says that, the question is, what qubits are good for different parts of computers, such as ALU, memory, or for quantum networking?
Oh, this is a very good question. I've said for a long time, maybe 8 years or more, our quantum systems will end up hybrid, I believe, if not just for quantum networking versus quantum computing, because the superconducting qubits or even ions aren't ideally suited to quantum networking. Ions emit, you saw this, that chart, they emit radiation in the UV. And we know that UV isn't going to go any distance at all in a fiber. So you need to convert it to, you need to do a flying qubit, that is the emission from an ion from the UV down to 1.5 micron communication wavelengths or 1.3 micron. And that has to preserve the quantum state when you do that conversion with some sort of optical parametric amplifier or something of that sort. And those types of things are being done, but it's not trivial. Likewise, it's also very non-trivial to convert up from gigahertz frequency to the multi-terahertz frequencies of the 1.5 micron photons. But that work is also being done, but it will require a different technology. Either way, you're going to have a different technology coming alongside your basic qubit technology to do what's called transduction between the basic qubit interface frequencies and that of long-haul telecommunication. So for quantum networking, there will be some hybrid technologies. Now, then you're asking about ALU and memory. Well, I wouldn't say that there's an ALU in a qubit. There are qubits that you use for computation, and there's no arithmetic logic unit equivalent. And memory, people have talked about qubit memory, and there again, some of these defects or ions can have nuclear states where you can park the quantum state for a longer period of time to preserve it. However, even those, there's a finite fidelity of moving it in from electron states to nuclear states and back again. And people are working on that. But again, I really think that another line of approach is to take superconducting qubits or other qubits and just add a code on it in order to create quantum memory. In fact, Shulkoff and Deborah's teams have used the cat codes and an automatic control to extend the lifetime of the cat states in their qubits. And they've demonstrated that better than I think any of these other technologies have right now. So what I'm saying is everyone's trying to find the answer to quantum memory. And I think in most cases, people feel that it's going to require some kind of coding to preserve the quantum state.
Great.
Other questions?
Other questions? I saw one hand raised, then disappeared again.
Hmm.
So, well, if you don't mind, I have another question.
Sure.
Now, for the superconductor qubit, right?
Mm-hmm.
So, if I'm asking, for scale up, error correction, all other things, what is the single biggest challenge, technical challenge you see down the road?
I think for all of these qubits that I've seen, I mentioned for ions, and I mentioned, I think for superconducting qubits, it's the 2-qubit gate fidelity is the single biggest issue. You may have heard of the use of dynamical decoupling, and in a trivial way, I can describe it like this. I'm going to go back, if I can go back to this chart, and it'll show you the complexity. For example, dynamical decoupling. Let's say in the case of a superconducting qubit, I'm pointing to this C0 gate, which is the entangling gate. And every qubit technology, depending on these entangling gates or other gates you use, will need to think of similar things. This gate requires a much larger amplitude RF pulse in order to cause the gate to function. And then if Q2 was a neighboring qubit of Q0, even though it's at a different frequency than Q1 that Q0 is talking to, it can still get perturbed. That's called this spectator qubit problem. It can be perturbed by the radiation you're using to control that entanglement. Oh, so you can fix that. You just put you split the C0 gate into 2 and do a square root C0, do half of it, do a pi pulse on this Q2, and do the other half of it. And when you do a pi pulse on Q2, any noise that accumulated on the first half, it undoes the noise on the second half. And that's called dynamical decoupling. And there are different ways to do this in different qubits. But from what you just heard, I'm adding lots of gates throughout these circuits to do that. So it actually makes the circuit longer. And that's not exactly what we want right now, to add a lot of length to the time, because we have finite coherence time and finite fidelity. So even these gates to do a pi pulse have their own fidelity hit. So there are many things that people are looking at, including this dynamical decoupling in various systems, like NV centers have tried dynamical decoupling, and many of the other qubits styles have as well, including the one I described in superconducting qubits. So making those 2-qubit gates accurate, have good fidelity without influencing the neighboring qubits, this is a big challenge for all of them.
Great. We have a question from Sang-Ho Om. Would you comment on the recent claims on quantum supremacy?
Yeah, so IBM prefers the term quantum advantage, and we are focusing our work on practical algorithms and not like these, like the Google experiment was very nice in the sense that it did show a quantum sampling problem that would be hard to simulate classically. In fact, it's exponentially hard with the number of qubits. But let me describe it this way so you understand what it was. If you shine a coherent laser and the beam expands a bit onto a wall, you'll see this speckle pattern. And that speckle pattern is due to the interference of different paths of that reflection as it's reaching your eye. And that speckle pattern would be extremely hard to compute because it depends on the detailed features of the surface from which the laser reflects. It's a quantum effect too, of course, because you have coherent light that's interfering. But in a similar way to the speckle pattern, what the Google experiment was looking for was signs of quantum states that have entanglement. So they're very hard to represent classically or simulate classically. And they were able to find in a part out of a million or something, I forget what the details were, they were able to find evidences of that kind of state existing that would be exponentially hard for a classical computer to simulate. In other words, they were saying our device is quantum, and it's hard for a classical system to simulate a quantum system that has that exponential number of states. And so they did demonstrate that their device was quantum, and it was hard to simulate, but it wasn't a useful advantage. Second, I believe it was Chinese Academy of Science boson simulator last year came up with a boson sampling problem that they claimed was even a greater separation between classical and their quantum boson sampling than was the Google case. And that may be true. I looked at their paper, and I think it's beautiful work. But again, boson sampling hasn't been proven to be useful for any practical problem that I'm aware of, though people have speculated that something like a boson sampling could be used to extend certain types of quantum sensing sensitivities. And there's a recent thesis on that in the last several years. So I'm saying that we would like to stick with advantage and not supremacy, and advantage meaning I can do something better, and better to be defined. It could be lower power, it could be faster, or it could be more accurate, or any combination of those things than our current classical algorithms. And so I haven't seen that demonstrated by anyone yet. And perhaps things will come in the next, say, 3 years. I think it's getting closer. I used to say 3 to 5, but I think people are actually finding problems that have separation in a complexity theory sense from classical problems. And one of those is machine learning. And I believe that people will find an initial problem that shows this separation from classical computers that maybe have some small intersection with a useful problem, right? And I think that'll happen within 3 years or so. But it's going to take quite a while to get to the point where we have error-corrected machines and general purpose algorithms that can exploit the quantum states that solve a much larger number of problems.
I see. We have another question from
Yeah.
David Liu. What kinds of the QC problems are for computer scientists to solve? It seems we are still focusing on physical aspects.
Oh, David, good question. But my talk was focusing on the physical aspects, but actually there are quantum problems to solve, computer science problems to solve already. For example, if I generate a circuit like the one I'm showing on the screen, and I want to optimize that optimization problem is a very complex computer science problem, except it has different constraints than our classical computers have. For example, on a classical computer, you don't need to worry about the fidelity of an AND gate. The fidelity is so phenomenally good, you know, it's 10 to the minus 20. In other words, a part in 10 to the 20 or so error. So you just assume it's a perfect gate. Well, you can't do that with quantum systems. And furthermore, I've told you that quantum systems, the state lasts for a finite time. You don't have to worry about that either in a classical computer. So in a quantum sense, you want to optimize the problem to take the fewest number of gates, but also the shortest time, and be aware of the time and the errors. The errors will have to be handled in the software control stack, and eventually in the compiler, you will have to have something that controls some error coding, which will be required in any of these qubit states, completely unlike most classical machines at a software level. So there are many aspects of computer science that people are already working on, including clear at the top, when I make an application, say, of optimization or quantum chemistry calculation, there are different ways to use the qubit states and encode it to optimally solve the problem of question. And that, in many cases, is a computer science problem, that translation from your problem to something that a quantum machine can solve, just like it's a compiler, right? Because in regular computers, when you compile from some basic language a problem into an optimal set of instructions, that's kind of what I'm talking about there. And then there are layers and layers of things below that.
Great.
Okay, yeah.
Do we have any other questions? Are we closed?
There's another one.
There's another one? Okay.
Oh, no, I see.
I didn't see that. Yeah.
Yeah, okay. Yeah, but I can say, yeah, there's one we covered. But I can say for people that are interested, if there are students on the line, in August 20th, there will be recordings of the IBM Quantum Machine Learning Summer School for 2021. And that'll be on that Qiskit channel or the Qiskit website that I showed. And in fact, there are quite a few people collaborating. Qiskit now is more than, as I understand, more than 50% contributions of professors and students not from IBM. So it is a true open source collaborative enterprise. Even one student, I can say, one student came up with a better compiler than our theorists had initially written into Qiskit. Well, we used that compiler. So it shows you that computer science can be used right now. And people are contributing in that sense, but it requires still an understanding of quantum information science to make contributions at this point. Are there any other questions?
Yeah, I couldn't figure out. Any other questions for audience? Students, experts? This is really wonderful, insightful lectures. I learned a great deal of it. I appreciate that. Okay.
Thank you very much.
Thank you. So let's thank our speaker today. Thank you.
Well, thank you, Mark. Thank you, Chan, for this fantastic session, which was both informative and inspiring. And so tomorrow we will have the final day of the summit, and we will continue at 9 a.m. Eastern. So thank you so much.
Very good. Thank you.